Today I'm going to go over the Chapter 3 Comprehension Check questions. Chapter 3 is all about atoms, and it also is introducing you to the periodic table. And we're going to get really familiar with this as the course goes on. But the first part is introducing to you to chemical symbols and the formulas that we use to represent the elements on your periodic table. Now, I have put up the first 18 on my board. There's actually on the periodic table in your book, I believe 118. And if you're using the Berean Builder's periodic table, that periodic table is actually a little bit out of date. And so there are a few new elements that have been added to the periodic table, and it's kind of fun to go and look it up, especially if you live in Tennessee like I do. There's a new element called technetium after the state of Tennessee that's added to the bottom of a periodic table. But those aren't on our book, and we're not going to use them for this class. So for this class, you're mostly going to concentrate on like the first 20. We will dabble with a few others. Some teachers or parents require their children or their students to memorize the first 20. I don't require that of my students. I do actually find that by the end of the year, you will actually already have learned most of the information for these elements on the periodic table without actually memorizing them. We've just used them so much, you will learn the information. On your periodic table, you're gonna have two letters, and this is called your chemical symbol. And these are on, mine look a little bit different than the book, but the two letters are either from its Latin name or its English name, and they're what we use throughout the course as an abbreviation, because this one is aluminum, or some parts of the world say aluminium, and you wouldn't want to write aluminum out every time, so we would just write AL. And so these are the chemical symbols. There are quite a few of them that don't look like the word. And what I mean by that is W is actually tungsten, even though tungsten doesn't have a W in it anywhere. And copper is actually Cu. And so that's because those elements, their symbol was derived from their Latin word. And those are elements that we've actually known about for a really long time. And so their symbols were given before English was being used. You will get familiar with quite a few of those, but they're kind of some weird ones, like mercury is Hg. So look through your periodic table and see if you see any of the ones that the symbols don't seem to match their English word, and they actually are going to be matching their Latin word. Now, in the book, above the chemical symbol on the periodic table is a number. On my cards here, it's below it. Frequently, it is right in the top center. And so for aluminum, it would be a 13. Hydrogen's 1. There's helium's a 2. And so that number above it, it is considered the atomic number, and that is telling me how many protons are in the element. So aluminum has 13 protons in its nucleus. Now, any element with 13 protons is going to be aluminum. If you'll remember that the number of protons in the element is what gives it its identity. It makes it who it is. So if it has 1 proton, it's going to be a hydrogen, because all hydrogens have 1 proton. If it has 2, it's not a hydrogen, it's a helium. And so in your book, those numbers are above it. So just don't get confused, because mine look a little bit differently. So the other number on your periodic table on these cards, it's up here. In the book, it's below. It's like these cards just swapped everything. But for hydrogen, you see below it, it says 1.01. And that is the atomic mass. And that is the average atomic mass of one atom of hydrogen is 1.01. And the units for that is a whole new unit for you. It's called the atomic mass unit. And so this one has 1, your book has 1.01, some books have 1.09997. It just, some different periodic tables are going to round that differently. So the periodic table in the Berean Builder's book has to 2 decimal places the atomic mass. And so it tells you the atomic mass of one atom of hydrogen. Now, it's an average, because we've talked about how some elements can have more neutrons or they can lose neutrons. And so it is an average number. So for like oxygen, oxygen has 8 protons and it has an atomic mass of 16. So that means the average oxygen atom has a mass of 16 atomic mass units. So question number 1 on the chapter 3 comprehension check asks you how many protons are in an atom of aluminum. So you're going to find aluminum on your periodic table, and you're going to find as you first start looking for these elements, it feels like you're searching forever, but you will learn where they are. And so aluminum is in the top right. So there's more here if you were to like envision it. So this is going to be the top right of your periodic table. And above it, there should be a number 13, which is telling me that every aluminum atom has 13 protons. Question number 2 is asking, what's the mass of the average chlorine atom in grams? If you look at chlorine, it's in the top right of your periodic table, and the mass in the book says 35.45. Now, this mass is not in grams. The masses on the periodic table right now are not in grams. They are given to you in a unit called an AMU, which is a very tiny atomic mass unit. And it's approximately the mass of 1 proton or of 1 neutron. And so this is approximately the atomic mass of like 35 protons or 35 neutrons, which if you look at chlorine, it actually has about that many in there. Now it's an average. The reason I say it's of a proton and a neutron is even though when you are massing atoms, you have electrons. Electrons have such a small mass, especially for this course, it's going to be negligible into these calculations. And so this is a tiny number. It's telling me it's the mass of about 35 protons or neutrons. And I want to convert this to grams. And so this is where we're going to get your first conversion factor that you need for chapter 3. So the conversion factor that you're going to need to know for this chapter is that 1.66 times 10 to the negative 24 grams is 1 atomic mass unit. And this is a tiny number. This would be like if I had point and then I had 23 zeros and then I had 166. So it's a super small number, is the grams of 1 atomic mass unit. Now, go ahead if you start keeping a card for this chapter, I would write this down. For my class, I let them keep a note card as we work through these things, and then they can use that on their tests. So write it on your 3x5 note card. This unit, you're gonna need it. And so if you put grams on top, atomic mass units cancels out, and you're gonna be left with your unit in grams. Now, as you put this in your calculator, you're gonna get used to putting these in, but this may be one of the first of these weird types of problems you've done this year, where we're having to put in times 10 to a negative 24 into your calculator. So as you do this, make sure and put this entire thing in parentheses when you put it in your calculator. So you would say 35.45, and you're gonna multiply it by, in parentheses, 1.6 times 10 to the negative 24. You do not have to do the divided by 1. That doesn't really matter. That's just an extra step. Now, as you put into your calculator, if you're not familiar with how this works, you can put in 1.66 and you can say times 10, and you can raise it with this little caret key thing to the negative 24th. Or you can put in 1.66 and you can use the E button. And E just stands for exponent to the negative 24th. Try it both ways and see which way you like. We are, as the course progresses, going to be using lots of scientific notation with large exponents. So find which method works best for you. And so when you do put this through your calculator, you're going to get a result of 5.88 times 10 to the negative 23rd grams. And as it has said earlier, it is a tiny number, but this is the mass of 1 atom of chlorine in grams. And so it's going to be super small. We say it's just the average, and you'll understand that a little bit later on. But really we say an average because the amount of neutrons in a chlorine atom can either go up or down a little bit. So it affects the number, but you're getting a really good estimate of the average mass of 1 chlorine atom. So like I mentioned earlier, when you look on the periodic table and it said for chlorine 35.45, that is the average mass of a chlorine atom. The reason I said average is because elements have isotopes. Isotopes are atoms that have the same amount of protons. So all chlorine atoms are going to have 17 protons, but you may have a chlorine atom that has 17 neutrons. Then you may have another chlorine atom that has 18 neutrons, and you may have a chlorine atom that has 16 neutrons. And so the number of neutrons can actually change in an atom. And so we're going to learn how to determine how many protons and how many neutrons and how many electrons are in an atom. So when you get into these problems, these are all written a little bit differently, and it's just a different way of writing the same thing. So if you have here, we have a fluorine, and fluorine is actually like on the top right of your periodic table. And fluorine this fluorine has an 18, and it's written usually small and in the upper left-hand corner. And so we call these numbers, so these are the mass numbers. Now, a mass number is the number of protons and neutrons. It's essentially the stuff that's in the middle of the nucleus. And like I said earlier, the electrons have such a small mass that they're almost negligible for dealing with when you add into the mass of the protons and the neutrons. So when we're looking at this number, this is telling me the protons and the neutrons. It is wanting you to go through, and it's going to say list the protons, the neutrons, and the electrons for each of these compounds. Now, fluorine, to tell how many protons it is, you just need to look at it on the periodic table, and it is going to have above it a 9. That 9 tells you that is the atomic mass. That is telling you the number of protons. If it has 9 protons in it, it's fluorine. So fluorine will always have 9 protons in it. The other rule that you have for this chapter is that the number of protons is equal to the number of electrons. So if I have 9 protons, I am going to have 9 electrons. Now, this is for elements on their own. As we start making compounds, this rule will change later on throughout the course. But for right now, the number of protons equals the number of electrons. If you think about it as charges, 9 positive charges take 9 negative charges to balance this atom out. Now, when you're dealing with neutrons, this is the one that confuses everybody. But if you'll remember, this number is the number of protons and neutrons together. So if there's 9 protons, there have to be 9 neutrons in this element. For part B, we have a 40 in front of an argon. An argon is on the right side of the periodic table. It is actually has an 18 above it on your periodic table. And so if you look at that, the 18 above argon on your periodic table is telling you the number of protons it has. So there are 18 protons in argon. Now for this chapter, if you'll remember, the number of protons and the number of electrons are equal to each other. So we therefore have 18 electrons. The other thing that we have to figure out is the number of neutrons. Now this 40 is telling me that in the nucleus, there are basically 40 particles. And I have 18 of them are protons, so how many have to be neutrons? Well, 40 minus 18 is 22. So there are 22 neutrons in here. And so just to check, these two numbers have to equal this 40. For part C, they wrote it differently. They wrote sodium instead of giving you the symbol. Now, sodium is one of those things that you're going to learn is actually its symbol comes from its Latin word, and so we have an Na for sodium. Now, sodium has an 11 above it on your periodic table. And so that 11 tells me there are 11 protons. If there's 11 protons, there are 11 electrons. And if in the nucleus there are 23 particles, 11 are protons, then there must be 12 neutrons. 11 plus 12, this makes that 23 that we're looking at. All right, this is another one that is written differently. These are just 3 ways of writing the same thing. Hg is mercury, and you're going to find it on your periodic table. It has a lot of protons under the number 80. Well, if it has 80 protons, I know it has 80 electrons. And then the other thing you have to figure out is neutrons. And so if there's 200 particles in the nucleus, I'm going to take away 80. That gives me a total of 120 neutrons in that mercury element. Question number 4 is asking what is the most abundant isotope of sulfur. And like I've mentioned earlier, these elements all have the same number of protons, but their neutrons can change. And I've tried to draw what sulfur should look like in your periodic table. You have a 16 on top and you have a 32.06 on the bottom. The 16 tells me that there are 16 protons and every sulfur atom has 16 protons. But the mass in the middle with the protons and the neutrons can change. And so this is an average. It's 32.06 is the average. Well, when you're averaging up sulfur atoms, the most abundant one is going to have the heaviest weight in the average. The number, and it's going to be for this one, you're going to round it to the nearest whole number to find the most abundant isotope. So 32.06 would actually round to 32. And the reason why is because in order to calculate the average, 32 must be the most abundant number put in. So to find the most abundant isotope, you're going to take this number and you're going to round it to the nearest whole number. And so that will tell you that there are more 32 mass like sulfur isotopes than any other. Now, when they calculated this 32, there clearly was some numbers bigger than that to make it be 0.06. So there were some sulfur atoms that had 33 neutrons in them, 34, or even a few more, but most of the sulfur atoms have 32 protons and neutrons. So I'm going to give you an example of how you can know making that rounding is the most abundant isotope. So let's say you take a test in chemistry, and we're going to take the first 5. We're going to take 5 tests, and you make a 90. You make a 90 on it 4 times, and you make a 92 on it 1 time. So to find the average of my test, I'm going to add them all up and divide by 5. So I get 452. And when I divide that by 5, my average is 90.4. Now, what is your most abundant test grade? Your most common test grade is a 90, but that 92 messed up the average just a little bit. And so we would round this down to the next whole number, which would be 90, and that's going to give me my most abundant grade. The next section of the chapter 3 moves on to talking about light. And I know it feels really like, how in the world does light, do we go from an atom to a light? Well, understanding light helps us understand the electron part of the atom. And the reason is, if we take the model of an atom, I'm going to draw the planetary model, even though that's not the most accurate model. It's the easiest one to explain kind of why we're now going to talk about light. But if you have an atom and you've got a few protons and neutrons in the middle, and electrons, we're going to say they orbit like planets around your atom. Now, electrons can actually, these are called energy levels or orbits. We're going to study more about that, but this is just a brief introduction into this. These electrons out here, we write with an E with a little dash, they can actually jump from orbit. They can go from one orbit to the next and go back to their original orbit. And as they're jumping from orbits, they're actually releasing light. And so if I have this electron up here, he gets excited, he comes to the outside of the atom, but it wants to come back down. As it makes that step back down, it's actually going to release energy, and it's going to come out as light. Now, The light that we can see from these depends on how big of a step this is. Some of the orbits have like a bigger step that it jumps down. And so as electrons are moving amongst these orbits or releasing light, depending on how they're moving, depends on the color of light that they produce. So we can actually take a compound and burn it, which we will do in lab, and hopefully you do it in your lab, and look at the light it produces, kind of like a firework, produces different colors of light. And then we can take that color of light and we can try to predict what that compound is based on how the electron is moving and what light it's producing. So before we can really do that, the book introduces you to a light wave and the parts of a light wave. So we have a light wave, okay? And just like kind of looks like a water wave for this drawing. And some of the things that you need to know are the amplitude, which is essentially the height of the wave. The amplitude can either be measured like from the bottom to the midline. The bottom we call a trough, or it can be from the midline to the top, which the top is called a crest. An amplitude for light depends on how bright it is. So if it's a very short wave, like wave amplitude is very small, it is not going to be very bright light. Now the bigger you make it, the brighter it's going to be. Kind of like sound, if you use an amplifier for sound, it makes this bigger amplitude and sound gets louder. Light can't get louder, so it gets brighter. The other part that you need to learn for light are wavelengths. And wavelength is measured from the top of one crest to another crest, or from the bottom of a trough to the bottom of the next trough. For wavelength, we use this really weird upside down Y symbol, and it's called lambda. You're gonna start to see a lot of Greek symbols used to represent things in this class. Now, one of the things about wavelength is it determines what color. So different wavelengths produce different colors. And so essentially, if I burn a sample of copper and it produces this green blue light, I can then say I produced a wavelength that's approximately 500 nanometers long because it's blue. So we measure wavelength, it is a length. So we measure it in meters, but it's very small. So we use nanometers to measure wavelengths. If you're standing in the ocean and you have waves and they have a really long wavelength, so they're really far apart, so their wavelength is a big number, let's think about how frequent those waves are going to hit you. Well, not that frequently if you're waiting a long time in between waves. The other thing is you can have waves that are really close together and they have a shorter wavelengths, and they're going to frequently hit you constantly. That's when you're riding the waves and you feel like you can barely come up for a breath because every time you pop up, another wave takes you out. So it's not surprising that we have a mathematical equation that we're going to use for this. And it is this, frequency, which is F, is C over lambda. So this is frequency, and this is wavelengths. And C is a constant, and write it on your card if you can't remember it, but it's actually the speed of light. E is a constant, it's the speed of light in air, and it's 3.00 times 10 to the 8 meters per second. And so this is a formula that we're going to be using to calculate it. Now, when you have 3.00 times 10 to the 8 meters per second and you've got it over a wavelength, we actually measure frequency in a new unit called a hertz. Now, frequency and wavelengths are what we call inversely proportional, which means as the frequency goes up, the wavelength goes down. So they work opposite of each other. As the wavelength increases, the frequency decreases. As the wavelength goes up, the frequency is going to go down, which makes sense. The longer the distance between the waves, the longer you have to wait before you get hit by another wave. Question number 5 says, what's the wavelength, and they tell you in nanometers, of violet light, which has a frequency of 7.89 times 10 to the 14th hertz. So we're going to be using this frequency equals C over lambda equation to calculate the frequency. It's a pretty simple equation. There's just a tricky unit conversion at the end. So they tell you the frequency in hertz. C is a constant. If you don't know it, write it down. And lambda is what you're looking for. Now, to rework this so that you're solving for a lambda, you're going to move lambda over here, and then you would divide by this. So it would rewrite like you would multiply the lambda and bring it over here. Now to get wavelength alone, you're going to divide by this on both sides. When I work through this to make sure my units, I didn't tell you this earlier, but a hertz, another way of writing out a hertz is a 1 per second. That's like 1 wavelength per second, like 1 wave hits you per second. And so that is going to be, like, we're going to need that because then seconds are going to cancel out and you're going to be left with your answer in meters. You get 3.8 times 10 to the negative 7th in meters. Because we're new to putting all this in a calculator, you have got to put the entire top in brackets, and I would put the whole bottom in brackets. So it would be like a bracket around the 3.0 times 10 to the 8th divided by, and then a bracket around the 7.89 times 10 to the 14th. Those brackets are going to keep you from making, or parentheses, sorry, are going to keep you from making so many mistakes when you put this in your calculator. Now, this is giving it to me in meters. The question is asking in nanometers. And so there is one more conversion factor that this book gives you. Not one more. There is another conversion factor for this chapter, and it is how many nanometers are in a meter. And 1 nanometer is 10 to the negative 9th meters. That's a 9. I'm actually running out of space. Didn't plan very well there. And so meters is going to cancel out, and you're going to be able to convert to nanometers. You cannot use King-Herod die for this because nanometers is not even on that acronym. So I've written it up high because I ran out of space, but 3.8 times 10 to the second nanometers is your wavelength of violet light. Question number 6. You need the spectrum in the book on page 76 for this. I'll try to add it above. But we have 2 lights. I wish I had a yellow marker to write it in, but you have a bright yellow light, and then we have a dim blue light. So we have 2 lights, and it wants to know which one is producing waves with a lower frequency and which one is producing waves with a lower amplitude. Now, amplitude, if you'll remember, is on brightness. So the larger the wave or the taller the amplitude, the taller the wave, the brighter the light. And so the question is wanting to know the lower amplitude. So a lower amplitude is going to be a dim light. So this one is going to have the lower amplitude. Now, the next part wants to know which one's going to have a lower frequency. If you'll look at the spectrum that I'm going to attach above, the spectrum has not frequency, but it has wavelengths, because wavelengths tell me color. Now, this kind of confuses people because this is asking about frequency, not wavelengths. But remember, as frequency goes up, wavelengths go down. So they're like inversely proportional. So if you're going to see that there is a blue light on the spectrum and it has about a 500 nanometer wavelength, and the yellow has about a 600 nanometer wavelength. So if it has a 600, the higher wavelength is going to have a lower frequency. They work opposite of each other. And so the yellow light is going to have a lower frequency.